What if I told you that the small, demoted planet at the edge of our solar system turned out to be one of the most active, surprising worlds we've ever seen? Welcome back to CosmoQuest 8888. If you enjoy calm, clear space science, no hype, just real context, tap like and subscribe. And stay until the end, because the biggest shock of Pluto wasn't what we saw on the surface. It was what those images implied about Pluto's interior. On January 19, 2006, NASA launched New Horizons on a one-way journey toward Pluto. 9.5 years later, on July 14, 2015, the probe raced past Pluto at incredible speed, giving humanity its first close-up look at a world that had been a dot in telescopes for generations. And right away, Pluto refused to behave like a dead, frozen rock. Let's set the stage. Pluto sits in the Kuiper Belt, a vast region beyond Neptune filled with icy bodies, remnants from the solar system's early days. In 2006, Pluto was reclassified as a dwarf planet, largely because astronomers found more Pluto-like objects out there, and the official definition of planet tightened. But here's the twist: the label changed. The science got bigger. Pluto is about 2,400 kilometers across, smaller than Earth's moon. But it's not just a single object in space. Pluto and its largest moon, Charon, are so closely matched that some scientists describe them as a kind of double world. They're tidally locked to each other, always showing the same face, like two dancers permanently facing one another as they orbit. From that distance, sunlight is weak. If you could stand on Pluto, the sun wouldn't look like a blazing disk the way it does from Earth. It would look like an extremely bright star. Temperatures hover around roughly minus 230 degrees Celsius, give or take, cold enough that gases we breathe on Earth can freeze solid. So, what should Pluto look like? Most people expected an ancient surface, heavily cratered, unchanged for billions of years. That's what many small icy bodies look like. Old scars, no surprises. New Horizons delivered surprises immediately. One of the most iconic features is the bright heart-shaped region. Part of that heart is a vast plain of nitrogen ice, smooth, bright, and geologically young. Young is the key word. A smooth surface with few craters suggests it's been resurfaced relatively recently on planetary timescales. Something has been renewing it. And that forces a question. Where does the energy come from? Because Pluto isn't warmed much by the sun, any activity must be driven mostly from within. Now let's talk about the mountain candidates that caused a serious rethink. Wright Mons and Piccard Mons, large dome-like structures that some researchers interpret as signs of cryovolcanism. Cryovolcanism is like volcanism in slow motion, on ice worlds. Instead of molten rock, the lava can be water ice mixed with other compounds, slurries that can flow when warmed, then freeze into solid structures. We've seen hints of this kind of process elsewhere in the solar system, like on certain moons of Saturn. But Pluto? That was not a sure bet before 2015. What makes these domes interesting is how unusual they look compared to classic volcano shapes. They have broad, complex depressions, and the surrounding terrain can appear lumpy or hummocky, like material that rose up, cooled, and deformed as it froze. Importantly, the region shows relatively few impact craters, which again points to a surface that isn't extremely old. In plain terms, something may have pushed icy material upward from below, building mountains from frozen eruption products. And if that's true, Pluto's interior must be warmer and more dynamic than many early models predicted. This is where the story becomes even more intriguing: the possibility of a subsurface ocean. Based on Pluto's size, density, and the way ice and rock might be layered, scientists have explored the idea that beneath Pluto's outer shell, there could be liquid water, perhaps mixed with ammonia, which acts like an antifreeze and lowers the freezing point. If an ocean exists, it changes Pluto from a simple ice ball into a complex world with internal chemistry and long-term evolution. At this point, quick question for you. Do you think Pluto is more likely to be powered mainly by radioactive heat inside its rocky core, or by tidal interactions with Charon over long timescales? Drop your guess in the comments, because your answer connects directly to how we evaluate other icy worlds too. Now, we should be careful here. Possible ocean doesn't mean confirmed ocean, and cryovolcanism candidate doesn't mean active today. What it means is that Pluto shows features that are difficult to explain without internal heat and some form of mobility beneath the surface. And that's already a huge leap from what we assumed before New Horizons. Because New Horizons didn't just photograph Pluto, it gave us a new way to think about the Kuiper Belt itself. Before this mission, many people pictured Kuiper Belt objects as small, inert leftovers, cold, quiet archives. Pluto still is an archive of early solar system material, but it's also a world with weather-like processes in slow motion, volatile ices that can shift, thin atmospheres that can expand and collapse over seasons, and surfaces that can be reshaped without liquid water on top. And remember, New Horizons didn't only observe Pluto, it also mapped Charon in unprecedented detail, revealing a surface that looks dramatically different, more water ice dominated, with its own history of fractures and resurfacing. Studying Pluto and Charon side by side is like comparing two experiments that started with similar ingredients but evolved differently. So what did we really discover at Pluto? We discovered that size is not destiny. A small world, far from the sun, can still have a rich geology, driven by exotic ices, internal heat, and long-term interactions between layers. That matters not just for Pluto, but for the bigger question. How common are active icy worlds in the outer solar system? Because if Pluto can stay interesting for billions of years, then the Kuiper Belt might be filled with worlds that are more complex than we've ever imagined. And that brings us to the most delicate topic: life. Could life exist on Pluto? On the surface, it's extremely unlikely. Too cold, too dry, too harsh. But if a subsurface ocean exists, and if there's a steady energy source, radioactive decay, chemistry at rock-water boundaries, or long-term heat retention, then in theory, simple microbial life becomes a discussion point. Not a conclusion, a discussion. The honest scientific position is, we don't know. We don't have direct evidence. But Pluto now belongs to a category of worlds where the question is meaningful, not absurd. And that's the real power of New Horizons. It turned Pluto from a trivia fact into a scientific frontier. Now, think about what happened here. A spacecraft launched in 2006 reached Pluto in 2015 and changed our understanding of an entire region of the solar system simply by getting close enough to see. This is exactly why future impossible missions matter. Orbiters around distant dwarf planets, landers on icy moons, probes that can drill through ice, or radio observatories on the far side of the moon. The biggest discoveries often happen when we stop guessing from far away and finally arrive. If you want the next episode to focus on Pluto's heart and how nitrogen ice can move like a slow glacier, or on the strongest evidence for and against cryovolcanism on Wright Mons and Piccard Mons, tell me in the comments. And if you've enjoyed this deep dive, hit like. It helps Cosmo Quest 888 reach the people who love thoughtful space science. In the next videos, we'll connect Pluto to the bigger story, the Kuiper Belt, extreme mission designs, and the future of deep space exploration. Until then, keep looking up and keep your curiosity calibrated to the data.